Check, check, check. Check, check. So, online students, can you hear me clearly? Online students, can you hear me clearly? Okay, thank you. Okay, so last Ross, can you hear me? Last Ross, can you hear me? Ranot, can you hear me? Okay, thank you. And sorry for the delay. I had to wait until everyone joins the class. Okay, because it is a new day. I had to wait. Okay, so everyone, please be silent. Okay, please be silent, everyone. Okay, okay, okay. Be silent, everyone. Stop talking. Everyone, stop talking. Okay, pay attention. Okay. Uh, I'm sorry for the delay because I had to wait until everyone joins the class because it's a new day and we are starting force and momentum today. Okay, we are starting force and momentum today. And for projectiles, pay attention. And for projectile, there's some other stuff happening. That means there would be some extra classes, especially tomorrow. So there will be a session like as usual. I'll be doing few other sessions continuously until you get really comfortable with projectiles. So projectiles and linear motion. Stop talking. Projectiles and linear motion is not over. Okay. Projectiles and linear motion is not over. We will have to keep doing questions again and again, additional classes, do some past paper discussions, and I'll explain everything like since still students are joining, I'll explain everything after maybe 5-10 minutes. Okay. And for new students, we are starting a new lesson today, and this is the English medium class, and you have a Sinhala and English medium class on Sunday evening. You have a Sinhala and English medium class. If you like, you can join that. And for the things that you have missed until now, there's another session going on called Mechanics from Beginning, where you can use that session to cover up whatever the things you have missed up to today. Okay, you can use that sessions to cover up whatever the things that you have missed up to today. So the initial parts that you have missed, don't worry about that. We'll be doing some other sessions to uh, clarify that issue. Okay, and there's some other stuff happening these days, but I'll inform everything like after starting the class. Okay, so okay, so force and momentum. Like until now, we discussed about motion, right? We discussed about motion. That means something going from point A to point B. Clear? Until now, we discussed about motion. That means something going from point A to point B. That is motion. Clear? Now, in this lesson, what we are focusing on is who decides this motion or what affects this motion. What affects this motion? So as we know, what affects the motion is, what is that? What affects the motion is definitely the force, right? The force. So here in this lesson, in force and momentum part, what we are going to decide is what affects the force, okay? What affects the motion, clear? And again, like your initial parts that you have missed have minimum effect on this part, but if there are like one or two issues due to previous parts, I'll do a separate session for new students to clarify those issues and to make sure that they can continue this lesson easily, okay? So there's like that kind of a plan going on. So like before starting anything, okay, before starting to discuss about force or anything, we should identify why do we need a force? Why do we need a force to move something? Why can't something start moving without a force? Why can't we do that? I mean, why can't even me, why can't I move from here to here without applying a force, without walking? Why can't I move, or why can't anything move, okay? Why isn't, I mean, what makes it difficult for something to move without a force? Clear? Without a force. The reason behind this is inertia, okay? Reason behind this is inertia. That means, like, who are the people who like knows how to ride a bicycle? People who knows how to ride a bicycle? Okay, there are people who don't know, right? Really? 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 Okay. Okay. So, so pay attention. So, if we discuss about like riding a bicycle, it's difficult to start moving, right? It's difficult to start moving, and when it pick up, when it pick up that motion, then it's easy to move. Then again, it's difficult to stop. That's how it works, right? Okay. When it is stationary, when the bicycle is stationary, it's difficult to start moving. Clear? When the bicycle is stationary, it's difficult to start moving. But then you somehow apply a force and start moving, then you can easily move forward, right? Then you can easily move forward. Clear? Again, same goes with anything. I mean, pay attention. Again, same goes with something like, assume you are pushing something heavy, maybe a table, okay? When the table is stationary, it's really difficult to start moving, right? You apply a higher force, you have to apply a higher force to start the motion. Clear? When there's a heavy table and you try to push that, okay? It's difficult to start that motion. It's difficult to start that motion when it is stationary. Clear? You somehow try to push that, okay? But after a certain threshold, it starts moving, right? It starts moving. When it starts moving, then it's easy. It keeps moving, right? Okay? It just keeps moving forward. Clear? It just keeps moving forward. Clear? So, there, what we see is a resistance for change. That means it's not in just objects, it's in everything. Okay? I mean, assume that you have to do some kind of a like homework. Okay? It's the most difficult part is get up and start doing that. And after that, like when you pick up the momentum, doing that is not that difficult, right? You have to do a paper starting. And how was the paper today? That's good, right? Okay. So, so it's like, it's difficult to like start working or start doing a paper at home. But when you start doing the paper, you don't have a huge resistance. You just keep doing the paper, right? Clear? So, attention, attention. In any natural scenario, then in any natural scenario, okay, in any natural scenario, there's a resistance to change. That means if something is happening currently, there's a resistance to change that. Clear? That means when the bicycle is stationary, it's difficult to move that. When the bicycle is moving, it's difficult to stop that. When a car is moving, you need a force to stop that. It just doesn't stop. And when the car is stationed, you need a huge torque, a huge power from a motor to move that. So there's in objects, there's always resistance for change. That means if it is stationed, it likes to stay stationary. And if it is moving, it likes to stay moving. Okay? This like requirement of like retaining its motion or this resistance to change in objects, we call that inertia. Clear? This resistance to change, we call that inertia. Clear? That's what we call inertia. Clear? So, like, there's a series of things that we can like explain. Like, move to your note, Mali, a tute. And anyone who didn't get the tute? Anyone? 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 Everyone got the tute, right? Okay. And for online students, tutes. We'll provide the tute for online students too. And for online students, tutes will be delivered, okay? Tutes will be delivered, especially new students. Send a message to this number, 070-154-6825. 070, thank you, 154-6825. Send a message to this number requesting for the tutes, okay? Send a message to this number requesting for the tutes. We'll deliver your tutes, okay? We're sending a set of tutes around like 150, 200 tutes tomorrow. So it's better if you can put the message now or before like the end of today so that we can make sure that we are delivering your tutes tomorrow with the other tutes, okay? So send a message to this number requesting for the tutes now, okay? Now. If possible now, if you have the mobile phone now or at least before the end of today, okay? And for many students, we have already sent the tutes, okay? Many students, they already have the tute. Okay, in your tute, go to the first page. In your tute, go to the first page. And online students, contact this number now if you need the tute. If you are in the Zoom chat, you won't find the tute. So contact this number to get the tutes. Fisher. Well, okay, so in the first page, attention, attention. In the first page, you have examples of inertia. Pay attention, stop talking, everyone. Okay, we have example of inertia. We have examples of inertia. That means one thing is, if a vehicle stops, it's difficult to start moving that. But when a set of people gather and when they try to push the vehicle, it's difficult to start the motion. But when the vehicle is moving, you just have to keep enough force to keep that moving. You don't have to force, right? Okay, it's difficult to start moving the vehicle, right? Again, you have seen this, okay? Again, you have seen this, like, you take a bottle, you take a bottle and a piece of paper, and you place a coin like this. You place a coin like this, okay? And you know, right? If you move this, attention, if you move this really slowly, okay? If you move this very slowly, the coin will move with the paper, right? If you move this very slowly, the coin will move with the paper. But if you move this piece of paper really fast, if you move this paper really fast, then this coin will fall into this bottle, right? Here you have that experience, right? If you move this paper really fast, this coin will fall into this bottle, right? Why? What is the reason? What is the reason? Inertia. Why? I'm applying the force on this piece of paper, right? I'm applying the force on this piece of paper. I'm not applying a force on this coin. And this coin has an inertia. This coin has an inertia. Clear? That means it tries to retain its motion. Clear? This coin has an inertia and it tries to retain its motion. Clear? It tries to retain its motion. Clear? That means when you move this, the coin will try to stay stationary. Clear? When you move this really fast, the coin will try to stay stationary. Why? I mean, there's no external impact. There's no external impact, so it tries to keep its motion, right? What is its motion currently? Currently, what is its motion? It's stationary, right? It's stationary. So the coin likes to stay stationary if it is stationary now. Clear? So all of a sudden, when you move this paper, the coin doesn't have enough time to change its inertia or change its motion. So the coin will stay there and it will fall down. Clear? Again, uh, like this is an A-level past paper. This question was there. You have a bit heavy object here. You have a bit heavy object here. You have a bit heavy object here. And you move this really fast. That means this is a string and you have connected the heavy object here. Then this is another string. This is another string. Clear? So like now tell me what happens if I move this string very slowly. That means I just apply a slight force and keep pulling this really slowly. Then what happens? What happens when you keep increasing the force? The string will break down from this point. The string will break down from this point. Then, if you apply a very fast force here, that means you are going to apply a really fast force here. Clear? Okay. You would pull this really fast. Then, nothing would happen to this string. Nothing would happen to this string. And this string will break. What is the reason? What is the reason? Again, inertia. That means this block has an inertia. Clear? This block contains a lot of inertia. Clear? This block contains a lot of inertia. Clear? Then, if you keep moving this slowly, there's enough time for this force to transmit up to this point. Why? Usually, this string will feel a higher tension. Why? I'm applying a force here. I'm applying a force here. And there's a weight. There's a weight to this block. Both this force and weight is felt by this string, right? Both this force and weight will felt by this string, right? So usually this string should break first, right? This string should break first. Why? Usually this force plus the weight both combined is felt by this string. Clear? So when you keep moving this really slowly, this force transmits and this string will feel a very high tension and it will break. Clear? And it will break. Clear? But when you move this string really fast, when you move this string really fast, when you move this string really fast, Now, for something to change its motion, they need enough time. Okay. Now, if you apply this force really fast, this mass, due to its inertia, it will stay there for a while. At least for a millisecond, it will try to stay there. Because any object likes to retain its motion. Any object likes to retain its motion. Clear? So this block will try to stay stationary for a while, at least for a millisecond. At least for a millisecond, this block will try to stay there due to its inertia. Every natural object, okay, okay, tries to retain its motion. Clear? Every natural object tries to retain its motion. Clear? Clear? So it will try to stay here. Clear? When it try to stay here, this string will feel nothing, right? Why? When it tries to stay here, this force will not transmit to this point, right? Why? When you pull this string tries to move down. But this mass, at least for a millisecond, rejects that. Why? Every object in nature tries to retain its motion. That's inertia. Clear? So you apply a very fast force here, and this block, at least for a second, tries to stay there. That means this acts as a wall. This acts as a wall. So as a result, this acts as a wall. So now all of a sudden, only this string is stretched and it's going to break down. Clear? Clear? Okay. So that's inertia. Okay. So if you don't provide enough time for this force to transmit and it to transmit up to this string, always this string will break down. Clear? This string will break down. Clear? Clear? That's the idea. Then, and again, like take maybe a leather ball and a tennis ball. I mean, it's difficult to move a leather ball, and again, it's difficult to stop it when it's moving. Okay, okay, that is a good example. I'll move to that later, because yeah, I'll explain it after this example. And you have seen these kind of stunts always, right? I mean, there's a person, okay? There's a person or something, okay? There's a person or something, and on that person, okay? This is a person, I don't know how to draw, okay? And like, now you place like, this is a person, okay? So then we place a like, maybe a wooden block or something, okay? Then we place a wooden block or something. Then we place something like a concrete slab or a stone like this. Then you have seen that we hit this setup with a hammer, right? Then we hit this setup with a hammer. You have seen these kind of stunts, right? Just notice, in all these kind of stunts, there's a heavy object between the person and that thing which feels that force. That means in a stunt like this, we hit this stone, okay? We hit this stone with a hammer, okay? It is a huge force. But between that and the person, there's a huge block, maybe a wooden block or something like that. Now, if you apply that force slowly, this person is dead, okay? If you apply that force slowly, if you provide enough time, and if you apply that force slowly, all this force will be transmitted to the person's body, okay? If you apply this force really slowly, if you give enough time, and if you apply that force, then there's enough time for this force to transmit towards this person. Clear? But when we hit by a hammer, that happens for a millisecond, right? The collision happens for a millisecond. Now the force is not there anymore, right? When you hit by a hammer, the collision happens for a millisecond. Then again, it's not there. You again hit, the collision happens for a millisecond, then again it's not there. That means that force is very sudden and it disappears. Clear? You apply the force and it disappears. So when that time is really small, when that time of applying the force is really small, what happens is this huge block, we feel like, we think that this is added weight. Okay? We think that this block makes things more difficult. Why? It adds more weight. No, the story is when the weight of this thing is huge, it is an object with a huge inertia. It is an object with a huge inertia. Clear? That means this wooden block or the concrete block, it tries to stay there for a while. That's what we call the inertia. Every object tries to retain its motion. So if it is stationary, it will stay stationary. Clear? So this block will try to retain its motion and it will try to stay stationary for a while. Clear? So when it tries to stay stationary, it's not pushing this person, right? So when you apply this force, the force will be felt by this stone, but this block rejects to move downward due to its inertia. Everything tries to retain their motion. Clear? It will try to stay there, so it will not push this person down. That means this huge impact will be felt by this stone, but will not pass towards the person. Clear? But instead, if you apply a force slowly, you apply the same kind of force, but for a longer period of time, then the person will be crushed, okay? For sure. Clear? So, if you are not providing enough time, objects will not change their motion. Clear? Objects will not change their motion. Clear? Okay. For an example, like assume that you are applying a huge force on a vehicle. If you apply a huge force on a vehicle slowly, vehicle will take some time and will start moving forward, right? But if you apply a huge force for a second or a millisecond, what happens? The vehicle will crash, right? Okay? Okay? Assume that huge force created in an accident. Okay? One vehicle is stationary, okay? One vehicle is stationary and another vehicle comes from this side and crash with this vehicle. Since this crash is sudden, other parts of the vehicle are not ready to move forward due to their inertia. Okay? Now other parts of this vehicle are not ready to move due to inertia. As a result, this will crash, right? This will crash and the vehicle would crash, right? But assume you apply an equal force, force, slow and steady, and you keep increasing. You keep increasing. Then what happens? When you apply a similar force, but you start low and keep increasing that force is transmitted slowly. So all the parts of the vehicle will pick up this force and they will start moving slowly, right? Then they will start moving forward. Clear? See? So the same force, if you apply it suddenly, only the back door of the vehicle would crash and other parts try to retain their motion and they will stay there. But the same force, if you apply slow and steady, all the parts of the vehicle will pick up the motion and they will start moving slowly. Clear? Okay, so these kind of concepts like inertia, qualitative stuff, we have to understand properly, because when it comes to A levels, after doing thousands of questions, again, you won't find it difficult, okay? You won't find it difficult to do mathematical questions. You will anyways get answers. Then a lot of students will miss these kind of stuff. Okay, not the mathematical parts, just like when you have to think. Okay, when you have to think using just physics without numbers. Clear? These kind of areas we have to understand properly. Okay. Then, now again there's a problem. Okay, why? Inertia is just a word. Again, we can't do anything with words. We again have to convert things into numbers to do any calculation, right? So there's a unit that we use, or there's a physical quantity that represents inertia. What is that? There's a physical quantity that represents inertia. What is that? Mass. Okay, the mass. That means mass is a measurement of mass is a measurement of inertia. Mass is a measurement of inertia. Clear? That means you have this idea, right? Higher the mass, more difficult to move that object, right? Okay. It's you can push a bicycle, but you can't push a huge vehicle, right? Why? The mass. Okay, the mass of that object. So the physical quantity that represents inertia is mass. Clear? Is mass. Clear? Okay. So then we know an object with 5 kilogram mass, and if you take an object with 1000 kilogram mass, that 1000 kilogram object would have a higher inertia. It's difficult for you to move that object, and it's difficult for you to stop that object when it is moving. Clear? Clear? So mass is the like measurement. Okay, mass is the way we measure inertia. Clear? That's how we measure inertia. Clear? Then there are two types of mass that we measure. Usually when we measure mass, and as we know, it's a fundamental physical quantity, and mass is measured in kilograms. Clear? Mass is measured in kilograms. Then there are two types of mass that we measure. Usually the main type that we measure, I mean in the industry or in day-to-day usage, what we usually measure is gravitational mass. What we usually measure is gravitational mass. That means what we actually measure is not mass, it's weight. That means take a spring balance. Take a spring balance. So when you take a spring balance, what do we measure? Do we measure the mass? No, we aren't measuring the mass. In a spring balance, we aren't measuring the mass. What do we measure? What do we measure? In a spring balance, what we measure is the weight, not mass, mg. There's a gravitational pull on anything due to mass, right? When there's a mass, there's a gravitational pull on that object, right? What we measure using this spring balance is this weight, gravitational pull on this mass. So as a result, if you measure this mass here, you would get a different answer. And if you measure this mass maybe on top of Everest, you would get another answer. If you measure this mass using a spring balance using at the moon, you would get another answer. Why? At different places, gravitational pull is different, right? Clear? And if you try to measure this in space, this will be floating. You would measure 0. If you take this spring balance and try to measure this, what this spring balance measures is the tension. Right? Tension felt by the spring. But if you measure this at space, all the objects are just floating, right? All the objects are just floating. Clear? When the objects are just floating, it won't create any tension here, right? It won't create any tension here. Clear? So you will measure 0. Clear? See? So gravitational mass is just an easy way of measuring the mass, but it actually don't give us the proper mass because it changes, okay? Because it changes with the gravitational pull, okay? It changes with the gravitational pull. Clear? Again, same goes with the electronic balance. Electronic balance also, what they measure is the weight. The electronic balance is pushed downwards by the gravitational pull on this object, right? The electronic balance is pushed downwards by the gravitational pull, right? Gravity pulls this down, right? So, like, this is gravitational mass, and it's not the absolute form of mass. It's just an easy way to measure things, okay? We don't have to be very accurate when measuring things in day-to-day life, right? Okay? We don't have to be that accurate when measuring stuff in day-to-day life, and in our day-to-day life, we don't shift between moon and earth, right? And you even don't even shift between here and Everest. You just stay in the ground level, right? So, like, measuring things using gravitational mass is okay, right? Measuring things using gravitational mass is okay, even for very complex scientific experiments. When we are in ground level, we know the gravitational pull, then it's okay, right? Okay? Then it's okay. We don't shift between, we don't do the experiment now here, then on moon, then next day on Everest. We are not going to do that, right? So no big issue there. Clear? But assume you need to measure the mass. And again, now the problem is, attention, now the problem you feel is, if the weight is mg, when g changes, the mass you measure will change, right? When g changes, the mass you measure will change, okay? When g changes, the mass you measure will change. Clear? Clear? Then, like, there's a nice solution that we use to get rid of this impact from G. What is that? This is a bit of an additional part. There's a nice solution that we use to get rid of this G. Actually, we are not aware that we are not doing it purposefully, okay? But there's a nice balance that we can use to get rid of this impact from G. What is that? Yeah. This one. Even the chemical balance looks like this, okay? Even the chemical balance looks like this, okay? Even the chemical balance looks like this. That means this kind of balance you have seen, right? And there's a small balance like this that we call the chemical balance. So this clarify that issue behind G. Why? Why? Here, how we measure things is, we put something here, and that is mg. And that is mg. Then we put a similar mass to this side, and that will be simple mg. Clear? Then we balance the moment. Right? So the same gravitational pull is felt by both sides, right? Same gravitational pull is felt by both sides, right? Clear? So when same gravitational pull is felt by both sides, gravity have no impact, right? Clear? So in moon, this G will change, but here also this G will change, right? So you will still find capital M and simple M properly, right? Clear? 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 So in this setup, since gravitational field affects both sides, this gives us a much accurate answer for the mass. Clear? But the problem is you can't use this when there's no gravity. Gravity have no effect here. Why? Gravity is felt by both sides. Clear? So if you put 3 5 kilogram units here to balance this, you know that this side is 15 kilograms, right? If you put 3 5 kilogram units here, you know that this should be 15 kilograms, right? But you can't use this system when there's no gravity, right? Why? When there's no gravity, this stuff will be floating and this one will be floating, right? So this rectifies the issue of gravity But you can't use this setup to measure the mass when there's no gravity. Clear? Clear? This rectifies the issue behind gravity, but you can't use this to measure the mass when there's no gravity. Clear? Ah. Then there are some methods that we use, especially in space and like in lot of scenarios. It is an additional part actually. Uh, I have mentioned everything with paragraphs and clear examples. It's good to read this whole tute, okay? It's good to read the whole tute, okay? Pay attention, pay attention. Uh, like maybe take a pendulum or a ruler. Okay, attention. Now take a ruler. I mean, this part is not entirely in the syllabus, but it's good to know this, okay? It's good to know this. If you take a ruler and spin this, okay? If you take a ruler and spin this, it will oscillate for a while, right? Do we have a ruler that we can do that without breaking the ruler? Would that work? No, it's not. Ah, yeah. So, pay attention. If you take a ruler, it would spin for a while, right? See? It would spin for a while. Clear? Clear? It would spin for a while. Attention. And even in this side, it will spin. Gravity have nothing to do here. It's just going to spin. Clear? So, okay, focus, focus. Ah, nice. Okay, great work. Okay, so when you take this and when you give an initial motion, how fast it oscillates and how long will it oscillate again depends on inertia. Okay, when you give a initial motion to this object, how fast it oscillates and how long will this oscillate, okay, depends on inertia. Clear? So usually there's a system like this. Usually there's a system like this that we use. There's a system like this that we use. It's clamped here. It's clamped here. Attention, stop talking. It's clamped here. And you put a certain mass to this point. You attach a certain mass to this point. Then this machine gives an initial oscillation. This machine gives an initial oscillation and it checks how fast the motion happens and how long will the motion happens, and it can calculate the mass, and this mass we call the inertial mass, and it is the most accurate form of mass. They haven't asked us to learn this part in the syllabus, but it's good to know how do we measure the inertial mass. Okay, this is the exact inertial mass. Gravity have nothing to do here. Clear? Gravity have nothing to do here. Clear? This oscillation is decided by its own inertia. What is inertia? Inertia means the resistance to change. Resistance that object shows towards change. Clear? Resistance that object shows towards change. Clear? So I have provided you lengthy paragraphs and good explanations about everything. Just go through the note, okay? That's enough. Just go through the note. That's enough. I'm just going in the path mentioned in the syllabus. So I have given a huge note about inertial mass, but they have asked us just to introduce that, okay? Just to introduce that. Attention. So like, just to clarify stuff a bit, what we usually do is, in some labs also you will find this, okay? In the lab, what we do is, attention, stop talking. Nowadays, this is an advanced electronic instrument that does everything and gives us the output, okay? It provides the oscillation, it provides the oscillation, it measures the time, it measures everything, and it gives us the value, okay? So this is an advanced electronic instrument. But even in labs, okay, even in labs, we have a similar, even in labs, we have a similar setup. There, what we usually do is we put some non-mass into this. We put some non-mass into this, maybe 1 kilogram. Then we check the, like, check the time for one period. That means for one oscillation. We put a non-mass here. We put a non-mass here. And when we measure time it takes for by this one for one oscillation. Then we again put a non-mass here. Then we measure the time for one oscillation. Then we again put a non-mass here and we measure the time for a oscillation. Then again we put another mass, like this, okay, like this. For non-mass values, we measure the time it takes for one oscillation. And the time it takes for one oscillation entirely depends on this, its inertia, okay? Time it takes for one oscillation entirely depends on its inertia. Clear? Clear? So, we recreate this curve, okay? Using these values, we create this curve, okay? We create this curve using these values, okay? And now, thank you. And now when you put a mass, now when you put a certain mass, and when you measure the time, using this curve, if you know the time for oscillation, you can measure the mass. See? Now using this curve, if you know the time for an oscillation, using that, you can measure the mass. Clear? Clear? So in the lab, if you find this instrument, what you would do is this, okay? What you would do is this. You do the experiment for a non-series of mass. You do the experiment for a non-series of mass. Then you measure the time. Then you plot the graph. Then you predict using the graph. Clear? Usually, attention, usually without plotting m and t, if you plot m and t squared, you will get a straight line, okay? That is an experimental result in a system. And how this happens, you will learn in the lesson waves and oscillation, okay? This motion, this is a repetitive motion or a simple harmonic motion. We are going to discuss that in waves and oscillation lesson. So everything you would understand in waves and oscillation. But for now, if you plot m and t squared, okay, instead of m and t, if you plot m and t squared, you will get a straight line. Then it is easy, okay? Then what you would do is, you put an unknown mass here. You measure the time for one oscillation. Then you get t squared of that value. Then you use the graph to find the mass. Clear? Okay, so this is like this part is not entirely in the syllabus. It's a bit out of the syllabus, but it's good to know what is gravitational mass, what is inertial mass. That gravitational mass is not accurate, but it's okay. But inertial mass is much accurate because inertial mass is the actual mass, right? Inertial mass is the actual mass. Clear? Clear? In spring balance, electronic balance, everything, what we do is we use the gravitational pull to measure the mass. That means mg. Clear? But in systems like this, we don't need gravity to measure the mass, so it gives us a better value. Clear? That is the conclusion up to this point. Okay. Okay. Like, write down if you have to write anything. And everyone got the weekly revision tute? Everyone got the week. Anyone who didn't get the weekly revision tute? And online, weekly revision tute in the Zoom chat. Any questions? Okay. Okay. Pay attention. Again, there's a topic called inertial frames. I'll move to that part later. When we are doing Newton's laws. Okay. Let's first learn the term called momentum. Did you have momentum in like O levels? Okay, then cool. What is momentum? Mass into velocity, right? Pay attention. Stop talking. Momentum is mass into velocity, right? mv. Uh, so mass is just a scalar. Mass is just a scalar. Clear? And velocity is a vector. Velocity has a direction, right? Velocity has a direction. Then momentum is a vector or a scalar. Definitely a vector. Why? I mean, when velocity, since velocity have a direction, pay attention. Since velocity have a direction, okay? Since velocity have a direction, definitely momentum should have a direction, right? Clear? Okay. So then, so one thing to know is this is a vector because it has a direction, and the direction of momentum is same as the direction of velocity. Direction of momentum is same as the direction of velocity. Then dimensions of momentum. This is m, mass. Dimensions of momentum, m, mass. Velocity, lt minus 1. Velocity, lt minus 1. It is mlt minus 1. It is mlt minus 1. Then, pay attention. Then, when we change the velocity of an object from v1 to v2, when we change the velocity of an object from v1 to v2, if the mass of the object is m, its momentum will go from mv1 to mv2. Clear? Its momentum will go from mv1 to mv2. Then what is the change in momentum? What is the change in momentum in this scenario? What is the change in momentum? mv2 minus mv1, right? Change in momentum is mv2 minus mv1. Clear? This is not the only way that momentum can change. This is not the only way that momentum can change. I mean, assume that there's a conveyor belt. Assume that there's a conveyor belt. And it contains some bags. Mass of these bags is capital M. Mass of these bags is capital M. And the conveyor belt is moving with a velocity of v. Conveyor belt is moving with a velocity of v. Now what is the momentum? Let's take this as m1. Now the momentum is mass into velocity, right? Which is m1v. Clear? Momentum is mass into velocity, which is m1v. Clear? Mass into velocity, m1v. Clear? Now, all of a sudden, a person put another bag onto this conveyor belt, okay, which changes the mass from, overall mass from m1 to m2. A person add an additional mass to this conveyor belt, which changes the mass from m1 to m2. Clear? It changes the mass from m1 to m2. Then what is the new momentum? I mean, usually the velocity of the conveyor belt will not change. Okay? Usually the velocity of a conveyor belt will retain, right? Somehow the motor will retain the same velocity. So velocity will be v. Then the new momentum will be m2v. New momentum will be m2v. Clear? Then what is the change in momentum in this scenario? What is the change in momentum in this scenario? Final momentum m2v minus initial momentum m1v. Clear? Final momentum m2v minus initial momentum m1v. Clear? m2v minus m1v. Clear? So this is the change in momentum. This is the change in momentum. Okay. Quickly go to exercise 1. And when you are writing the change in momentum, you should consider the direction. In what direction are you considering the change in momentum? Why? Momentum is a vector. So change in momentum should have a direction too. Clear? Clear? Then go to exercise 1. Go to exercise 1. Question 2. Question 4. Question 5. 6 and 7. Quickly write. Quickly write answers. Quickly write answers for these questions. Mali, tute into the Zoom chat. Okay. Exercise 1, question 2. As a 3 kilogram object travels over a rough surface, its velocity decreases from 10 to 6. What is the momentum difference in that direction? So, mass of the object is 3 kilograms. Mass of the object is 3 kilograms. It goes from 10 to 6. It goes from 10 to 6. What is the momentum difference in that direction? So again, what is the momentum difference in this direction? Delta P. Always difference means final value minus initial value, right? Difference means final value minus initial value. So P2 minus P1. What is the final value? This. Final value is this. So MV2 minus MV1. Then what is the mass? Mass is 3 kilograms. Mass is 3 kilograms. Here the velocity is 6. Here the velocity is 6. Minus, again the mass is 3 kilograms. Initial velocity is 10. Initial velocity is 10. So final momentum minus initial momentum, clear? Which gives you 18 minus 30. This gives you 18 minus 30, which means minus 12. Minus 12. Unit, what is the unit of momentum? Kilogram meters per second. Kilogram meters per second. So the change in momentum in that direction is minus 12 kilogram meters per second. Clear? And again, tomorrow evening, I'll be discussing like last week, Friday evening, I did all the recordings are available in the WhatsApp group. Last week, Friday evening, I discussed projectile tube. And the week before that, also in Friday evening, I discussed another projectile tube. Tomorrow evening, from tomorrow onwards, Friday evenings, whenever possible, I'll be discussing term test papers, okay? So tomorrow evening, I'll discuss the term test paper. I'll inform the time and term test paper. These are extra classes, so we can't arrange predefined time whenever I don't have a meeting. Like, I schedule a meeting and like do the class, okay? So usually on Fridays, what I'm doing is like my company work. So when I don't have like any company work or meeting, I will arrange a time and do every Friday. I'll try to do at least one term test paper discussion. So tomorrow there will be a term test paper discussion, okay? Tomorrow there will be a term test paper discussion. And for new students, for now, this Sunday, we are starting from 9 to 11 online. Mechanics from beginning, we are starting motion. We are starting motion again on Sundays night 9 to 11. This Sunday also from 9 to 11, we will be starting the mechanics from beginning session and we'll be starting motion. We finished vectors and we'll be starting motion. And if someone need, I'll provide the vectors recording too. We did 4 sessions for vectors. I'll provide those 4 recordings in the group today. And next Sunday, we are starting motion in mechanics from beginning sessions. So anyone, any new student can use them to cover up the missed parts. And also if they like, they can request for the recordings too. We'll provide you the recording, okay? So to get added to the group or to get recordings, contact this number, okay? Not 7015546825. Contact this number to get tunes delivered, to be added to the group, or to get previous recordings, okay? So question 4. Question 4. Question 4. Uh, there's an object, 5 kilogram, velocity 4, velocity 4, then 3 kilogram, 3 kilogram, velocity 0, velocity 0, then they get combined, 5 and 3, they get combined, and the velocity is again 4. Again, the velocity is 4. What is the initial momentum of the system? Stop talking. What is the initial momentum of the system? This is the initial situation. 5 into 5 into 4, 5 into 4 plus 3 into 0. 5 into 4 plus 3 into 0. So initial momentum is 20 kilogram meters per second. Then the new momentum, this is the new scenario. New momentum is both 5 and 3 are moving with a velocity of 4 now. So both 5 and 3, mass into velocity. Both 5 and 3 are moving with the velocity of 4. Both 5 and 3 are moving with the velocity of 4. Then 32. 32. 32. Then what is the change in momentum? Change in momentum is P2 minus P1. Change in momentum is P2 minus P1, which is 32 minus 20. 32 minus 20. Change in momentum is 32 final momentum minus initial momentum, which is 32 minus 20, which is 12. 12 kilogram meters per second. Change in momentum is 12. 12 kilogram meters. Okay. B with the 3 and after the question, both objects move in original velocity. In the question, they are telling that it's 2, right? That's the only difference, right? Okay. So according to text, if we move according to text, velocity goes down to 2, right? Velocity goes down to 2. Then what is the answer? If the velocity goes down to 2, this is 16. This is 16. Then this is 16. 16 minus 20. This gives you 16 minus 20 gives you minus 4. 16 minus 20 gives you minus 4. I just worked according to the text. Although you have 4 here in the diagram, in the text they are telling that it's 2. So we can go with that value. In the text they are telling that this value is 2, not 4. Question 5. Question 5. So tomorrow I'll be starting with, I mean, I was able to find enough, like, not enough, I need more, but at least I was able to find like Anand College papers and Royal College papers and Devi Balika papers too. Someone send me those papers. If possible, send me more papers, especially from your school. Okay, because if you need me to discuss term test papers from your school, it's better to send papers, okay? So try to find some term test papers and send. From tomorrow onwards, I'm starting the term test paper discussion, okay? Uh, this is 5 kilogram and velocity is 10. And this is again 5 kilogram. This is again 5 kilogram and the velocity is 2. After the collision, they collide. Both objects move in the same direction with a velocity of 4. So after the collision, both objects move with the same velocity of 4. Moves with the same velocity of 4. Attention, stop talking everyone. Stop talking. Okay, so what is the initial momentum? What they're asking is initial momentum of the system, final momentum of the system, change in momentum. So initial momentum, P1, I would write all the momentum values in this direction, okay? Stop talking. I would write all the momentum values in this direction. Uh, so P2 is, sorry, initial momentum, let's take as P1. P1 is, this is the initial scenario. 5 into 10, 5 into 10 plus 5 into, this should be minus 2. See, why? This is my positive direction, okay? This is my positive direction. If this is my positive direction, if this is the positive direction, this velocity is in opposite direction. This velocity is in opposite direction. So it should be written as minus, right? It should be written as minus. Clear? So the overall momentum is here 5 into 10, 50. Here 5 into 2, minus 10, which is 40. Which is 40. Then pay attention everyone. P2, second scenario. Both 5 and 5, overall mass 5 plus 5, moves with a velocity of 4. Moves with a velocity of 4. Both mass moves with a velocity of 4. So the momentum is again 40. Again 40. Clear? Again 40. So what is the change in momentum? What is the change in momentum? Delta P. Change in momentum is P2 minus P1. Change in momentum is P2 minus P1. So final momentum is 40. Initial momentum is 40. So there's no change in momentum. There's no change in momentum. 40 minus 40 equals 0. Clear? There's no change in momentum. Clear? Then question 6. Here the change in momentum is 0. Next question 6. Yeah, the cover-up classes for initial like discussions, the mechanics from beginning sessions will provide all the details in the group, okay? So make sure you are in the group, okay? Make sure you are in the group. Okay. Question 6. Question 6. And again, pay attention. If anyone have doubts up to this point, that means like if you at least do pay attention, everyone, stop talking, front rows. So like if anyone having doubt, I mean if you try some questions and if you have any doubts, I mean the invigilating program is going on, but we are going to make it much neat. So we will again provide you the schedule for that. So online students can contact our invigilators through Zoom, and we will like through WhatsApp, and will provide you a Zoom link so that they can clarify whatever the issues you have through the invigilating program. And for physical class students, we'll provide a schedule. Within that schedule, anytime you can come to the institute and ask questions, okay? You can come to the institute and ask questions. I mean, if all of a sudden we get a lot of traffic for a day, it would be difficult to cater, but from next week, we'll again increase the number of invigilators, okay? So for now, we'll provide you the schedule. You can work, like at least try a term test paper. Then when you have questions, you can come in a given time slot, okay? In whatever the time slot, you can come to the class physically, or you can contact our invigilators through WhatsApp and get a Zoom meeting arranged. Then you can clarify those issues, okay? But the best thing is physical students try to come physically if possible, because then it's easy to us to manage things, okay? So the invigilating program, we will make it much neat. We will provide you all the schedules and everything. Use that in a meaningful way, okay? Okay. Question 6. Question 6. An object of mass m moves with a velocity u and hits the wall perpendicularly. The object bounces back with the same velocity. What is the change in momentum caused by this collision? Uh, so mass is m, velocity is u. Mass is m, velocity is u. It collides. Pay attention, everyone. Stop talking. Mass is m, velocity is u. I know that when the questions are easy, you start talking, but it's not fair because at least one or two students are listening. Okay, so intelligent and selfish is the worst combination. Okay, you can have. So then again, after the collision, it bounces back. After the collision, it bounces back. Okay, it moves with the velocity of u, and it returns with the velocity of u. Then when you are writing the change in momentum, you should choose a direction for the change in momentum. Here, as you see, finally momentum is in this direction, right? Finally, the momentum is in this direction, right? That means the change in momentum is in this direction, right? Change in momentum is in this direction. Clear? So, in this direction, I choose this as the direction for the change in momentum. Again, change in momentum means final momentum minus initial momentum. Change in momentum means final momentum minus initial momentum. So, final momentum is mu in this direction. Final momentum is mu in this direction. Both are in this direction. This is my chosen direction. Initial momentum is m, and the initial velocity is in that direction. Initial velocity is in that direction, but my positive direction is this. Initial velocity is in this direction, but my direction is this. So I have to write it as minus u. So I'm going to get mu. Minus and minus gives me plus mu. Minus and minus gives me plus mu. Then 2 mu. 2 mu. This is the change in momentum in this direction. 2 mu in this direction. Clear? So the direction matters, okay? Direction matters. Next. Question 7. Question 7. Okay. Question 7. Mass is m and it moves like this. After the collision, this angle is alpha. After the collision, it bounces back like this. After the collision, it bounces back like this. So at the moment, velocities are u and u. So the momentum in this direction, is mu. Momentum in this direction is mu. And here, the momentum in this direction is again mu. Clear? Momentum in this direction is mu. And here, momentum in this direction is mu. Clear? Clear? Now, they are specifically considering 2 directions. So I'll break everything into those directions. So, this is the wall. Initial momentum is mu. I can break this into 2 directions like this and like this. Clear? And this angle is alpha. Now resolving vectors. How do we resolve vectors? This is mu cos alpha. So if someone don't have the idea about resolving vectors, they can watch the mechanics from beginning session, day 4, last session. We did resolving vectors on that session, okay? I'll provide all the recordings in the group, so make sure you are in the group. Physical students and online students both, make sure you are in the group, okay? I'll provide all these references in the group. So mu cos alpha, when you are going through the angle, it's cos. Then this is away from the angle. This is away from the angle, which is mu sin alpha. This is mu cos alpha. This is mu sin alpha. Then after the collision, again this is alpha. Momentum is mu. Momentum is mu. I can resolve this into 2 directions like this. This and this. Then when you go through the angle, again mu cos alpha. Mu cos alpha. Away from the angle, mu sin alpha. Mu sin alpha. So now, in this direction, initial momentum is mu cos alpha. In this direction, initial momentum is mu cos alpha. final momentum is minus mu cos alpha. Final momentum is minus mu cos alpha. Why? Initially, momentum is in this direction. Clear? After the collision, momentum is in this direction. In opposite direction. Clear? Then it should be minus, right? Minus mu cos alpha. So this is P1, initial momentum. This is P2, final momentum. They are asking the momentum in this direction and this direction. So let's choose those directions. So in the first one, the direction they are considering is downward direction. Downward direction. So final momentum, P2, final momentum in downward direction, P2, is this, right? Final momentum is this. Its downward component is mu sin alpha, right? Its downward component is mu sin alpha. Then initial momentum is this. Its downward component is mu sin alpha, again downward, mu sin alpha. Then 2, in this direction. Final momentum is this, P2, it is in this direction. See? Final momentum is in this direction, mu cos alpha. It's mu cos alpha. Then initial momentum in this direction is, this is the initial momentum. Initial momentum in this direction is minus mu cos alpha. Minus mu cos alpha. Why? It's in opposite direction. That's why. Initially mu cos alpha is in this direction. So momentum in this direction is minus mu cos alpha. So change in momentum, P2 minus P1, which is mu sin alpha minus mu sin alpha, minus mu sin alpha, which is 0. Then in this direction, change in momentum delta P is, change in momentum in this direction is P2 minus P1, final minus initial, P2 minus P1. Change in momentum is P2 minus P1. Final momentum mu cos alpha minus initial momentum is minus mu cos alpha. Minus mu cos alpha. Mu cos alpha minus mu cos alpha. Which gives you mu cos alpha minus plus mu cos alpha. This gives you 2 mu cos alpha. This gives you 2 mu cos alpha. Clear? Change in momentum. Pay attention. So there's no change in momentum in this direction. Momentum is retained. But there's a change in momentum in this direction. 2 mu cos alpha. Clear? Quickly do write and ask if you have any questions. Yeah, there's a request for a softball cricket match. Yes, would happen after 25 A levels because we had to include 25 people. I mean, the problem is like if we have the match tomorrow, they would skip A levels and come for the match. So, so yes, a softball cricket match or something like that would happen, but after A levels. So within like after 1 month. What is the reason for the mass time graph to be linear? When t is squared, you will learn in waves and oscillations. It's related to waves and oscillations. On something for Children's Day. When is the Children's Day? October 1st, right? I think, right? Yeah. And like, are you children now? Like, what is your age? 17 or 18? 17. Okay, okay. I mean, really close to be adults, right? And there's something about my haircut. I never know what I do in my hair. So, like, they decide. So, I go for the haircut and they do whatever they need and I go. That's what happens usually. Okay. Attention. Next, pay attention. Like, next, I have to do forces and Newton's laws. Do you need the interval before that or after that? Fi- Okay, so I'll give you the interval, but it's 5:57 at 20 to 5:57. What do we get when we at? Okay, it's okay. I'll start around 6:15, 17. Okay, 18.
So, so this is the sport meet season, right? නැද්ද මේ කාලේ නෙමෙයිද? නෑනේ. තාම මාසයක් අවුරුද්දයක් ගන්නනේ. While others come to the class, try to finish the exercise, okay? Try to finish exercise 1. Finish the whole exercise 1. You have only few questions remaining in exercise 1. Try to finish that, okay? And if you have any questions, please ask. Okay, let's start with the new part. Force. Force. That means until now we were discussing about changing the momentum, right? Pay attention, everyone. Stop talking. Focus. Quickly come to the class, everyone. Okay. Okay, now pay attention, everyone. Please be seated. Stop talking. New part, force. Force. So until now, what we discussed was like what is momentum, what is inertia, and that there's a resistance for change in any object, right? There's a resistance for change in any object. Then who changes, okay? Who changes this motion? So if there's a resistance to change, okay? If there's a resistance to change, there should be something that works against this resistance and change the motion. That is force. That is force. So Force is the effect. Force is the effect that changes the motion. Clear? Okay. Then I explained this previously. Pay attention, stop talking. I explained this previously. Force is a vector, right? Definitely force is a vector. Why? I mean, for something to be a vector, its final impact should depend, on its direction, right? So, if you apply a force in this direction, it will move in this direction, right? If you apply a force in this direction, it will move in this direction. Okay? So force is a vector. Why? Its final result depends on the its final result depends on the direction. So force is a vector. Now, force is a, pay attention everyone, front rows. So force is a vector, but it's a special type of vector. Why? Force is a vector, but it's a special type of vector. Why? What is the reason? Magnitude and direction doesn't tell everything about a force, right? Magnitude and direction, pay attention. Magnitude and direction doesn't tell everything about a force. Why? It's a special type of vector which isn't complete only with the magnitude and direction. Why? The reason is, yes, in a force, magnitude matters. Okay? And definitely direction matters. Direction matters. Whatever the final impact is decided by the direction. But again, there's another component of a force, that is point of action. Point of action, which means, or line of action, which means final result of a force depends on the point of action. That means where you apply the force. Why? See a system like this. You apply a force like this. Same force, 10 Newton in that direction. What will happen? It will move like this. If you apply a force like this, it will move like this, right? Clear? But if you apply the same force here, you take a pencil and apply the force to this end. You take a pencil and apply the force to this end. What happens? It tends to rotate, right? It tends to rotate. Clear? And again, you apply two equal forces like this. You apply 5 Newton and 5 Newton like this. Then the object will be stationary, right? Then the object will be stationary. You apply 5 Newton and 5 Newton in opposite direction, then the object will be stationary, right? Because no resultant force. There's no resultant force. So the object will be stationary. Object will be stationary. But if you apply these two forces like this, what happens? 5 Newtons and 5 Newtons. If you apply these two forces like this, what will happen? It will rotate, right? See, you apply the same force into the middle, nothing happens. You apply same forces here and here, then it rotates. See, same force, same directions, but point of action decides the output. So vector force is a special type of vector. Force is a special type of vector that the output depends not only on the magnitude and direction, but with the point of action too. Clear? So if someone asks you to define a force, you should define magnitude, direction, and the point of action. That means you should tell where should you apply the force. Clear? You should tell where should you apply the force. Clear? Okay. Then there are different types of forces: gravitational force, electromagnetic force, strong nuclear forces, weak nuclear forces. There are different types of forces. Okay. You don't have to study them, okay? But just know gravitational force means this thing falls down due to gravitational force, right? When I release something, it falls down due to gravitational force. Then electromagnetic forces are there. There's forces between charges, right? Positive charges attract negative charge. Negative charge attracts positive charge, right? These are electromagnetic forces. Then again, strong nuclear forces we will discuss in the last lesson, matter and radiation lesson. Strong nuclear forces. And weak nuclear forces, same. Weak nuclear forces we'll discuss in the uh, last lesson again. Then there are different types of forces, okay? These are the nature of different forces: gravitational, electromagnetic, strong, weak. These are types of forces, clear? These are types of forces, clear? Then there are different categories of forces. That means different categorizations of forces. One categorization is contact forces. Front row, pay attention. One category is contact forces. Okay, there are different types of forces. One is contact forces, and other one is field forces. What are these contact forces and field forces? You take this pencil, I can't move it horizontally without touching that, right? I can't move this pencil horizontally without touching that. So it is a contact force. The force should contact, clear? It is a contact force. Force should contact, clear? Then there are field forces. Field forces are, okay, field forces are, I mean, when I release this, it just fall, right? No contact on this. If I release this, it just falls down, right? Clear? No contact on this. That means gravitational force is contactless. See, gravitational pull is contactless, right? When I release this, it just accelerates down. Clear? Gravity, like there's no contact between Earth and this pencil, but it goes down, right? So field forces like gravitational forces, electrostatic forces, magnetic forces, clear? Magnetic forces, these kind of forces, okay? These kind of forces are uh, contactless forces, or we can call them field forces, clear? These type of forces are contactless forces or field forces, clear? Okay. Then we have pseudo forces, or we can tell them virtual forces, pseudo forces or virtual forces. What are pseudo forces or virtual forces? Pay attention. What are pseudo forces or virtual forces? These are not real forces, but you feel them. These are not real forces, but you feel them. For an example, now you are standing in a bus. You are standing in a bus. Okay. You are standing in a bus. Now, this bus is moving with a certain velocity, okay? This bus will be moving with a certain velocity. Now, all of a sudden, it applies a brake. What happens? This person will be, I mean, would move forward, right? Okay. So, if the bus moves and suddenly brakes, okay, this person will be pushed towards the front of the bus, and from the perspective of that person, he feels a force. Why? He was peacefully going in the bus. Now all of a sudden, he's pushed forward, right? He is pushed forward. Clear? So from the perspective of this person, okay, from the perspective of this person, he feels a force, right? He feels a force. Otherwise, I mean, how can he move forward all of a sudden without any reason? But for a person who sees the reality, a person who see from the ground, he understands what is happening here. He knows that nobody applies a force on this guy. It's just the bus was moving and the bus brakes. As a result, this person's body has already have a velocity. I mean, when this person is in the bus is also moving with the same velocity, okay? Bus is also moving in the same velocity. Now, all of a sudden, the bus applies a brake. Now, the velocity of the person, I mean, the bus have its own brake pads, right? Bus have its own brake pads. That's how the bus stops. But for the person, in this case, he don't have any mechanism to apply brake. So his velocity retains, again inertia. Velocity in his body retains, so he is pushed forward. But actually nobody is pushing him. It's just he had a velocity and bus stopped. There's no force involved here. So from the point of view of this guy, there's a force, but actually there's no force. We call these kind of stuff pseudo forces. Okay, it's just they feel that. They feel that there's a force, but there's no force. Clear? Same happens like I mean, I can tell many examples. Assume that a vehicle is taking a bend. A vehicle is taking a bend. Now, for the people who are inside this, they will feel like they are moved towards this direction, right? If a vehicle takes a bend, you will be pushed towards this side, right? If a vehicle takes a bend, okay? If a vehicle takes a bend, okay? You will be pushed away from this bend, right? Again, you think that there's a force, but it's not a force. What happens actually? What actually happens is, at the moment, I mean, we will come up with a better definition for this when we are doing repetitive motion, sorry, rotational motion. But for now, vehicle have its wheels, right? So as a result, vehicle have a mechanism to get this motion. Clear? But for the person, there's no mechanism to take the bend, so he tries to move in a straight line. He tries to move in a straight line, right? Because the vehicle have its own wheels, so the vehicle takes the bend peacefully. Clear? But for the person, there's no mechanism to complete a circular motion, so he tries to move forward. His velocity is in forward direction, right? Now what happens is, when the vehicle is here, person tries to go here. As a result, he collides with the door in this direction, and using that force from the door, he retains his motion. See? So when a vehicle is taking a bend, nobody pulls the person out from the bend. What happens is, vehicle goes in the bend and the person tries to move forward. As a result, see, as a result, he collides with the door of the vehicle, and from that collision, he get the capacity to move in this motion. Clear? Clear? So like that, when a person is in an accelerating system, clear? These are accelerating systems. When the vehicle stops, it decelerates. This is also an acceleration, kind of. Okay, we'll discuss it later. So when a person is in an accelerating system, pay attention. When a person is in an accelerating system, okay, they feel a force. These forces actually does not exist. Okay, these are just felt by that person. Clear? Clear? We call them pseudo forces or virtual forces. Okay, these are virtual forces. Clear? Clear? These are virtual forces. Okay. After finishing Newton's laws, we have to learn 3 Newton's laws. After finishing 3 Newton's laws, we'll do another discussion about this. Then I can explain things in a better way, okay? I can explain things better when we finish Newton's laws, okay? Then we can use mathematics for this and explain things properly. For now, just try to understand that, okay? So there are pseudo forces. Only the person feels that such force does not exist. Clear? Clear? Okay. Next one. Next one. And again, like one more thing is when it comes to A-level classes, usually the culture in my classes, I ask you to do whatever you need if you understand the concept. But the thing is, when I mentioned that focus or like ask you to listen for something, definitely do that. And in other classes, also sometimes teachers don't do that. They would just keep teaching. Okay, they would just keep teaching. Pay attention, everyone. They would just keep teaching, but never miss a detail. Okay, in A-level classes, never miss a detail. Why? At the beginning, like when the things are simple, I mean, when you don't have a lot of content, okay, this is related to all three subjects, okay. When you don't have a lot of content, when you understand the maths part, when you can do calculations and get answers quickly, there's a tendency that you start thinking that you're smart, okay. You're not actually smart, okay. There's a tendency that you're going to think that you're smart, then you're going to stop listening and you're going to do whatever you need. I'm okay with that because in my class, I have created an infrastructure where you can do whatever you need. If something is important, I mention that. But in many classes, they don't do that. They just keep teaching. Okay. Then there's a tendency that you're going to miss small points here and there. And these small points, when it when it's accumulated, when it accumulates for 2.5 years, now it's a huge amount of small points that you were not listening. Now you miss 5 or 6 MCQs, and 5, 6 MCQs means your district rank would go down by around 100, 150. Your island rank would go down by 600, 700 units, okay? Then you do second shine. Okay, then you do second shy, and we have seen more smart people doing second shy. Okay, I mean, they're not smart actually, they assume they are smart. Okay, we have seen more smart people do second shy than the mid-level people, because the mid-level people never miss a detail. The mid-level people never miss a detail. People who think they are smart, they miss us a lot of points. As a result, they move to the second shy, and you should see a 25 batch class. That means where revision students come. That means second shy students come. Second shy students even doesn't dare to talk when we are teaching for, if we teach for 8 hours, they would continuously listen for 8 hours. Okay, why? These second shy students are the students who missed maybe University of Moratuwa by 2 MCQs, missed medicine by 1 MCQ, missed engineering by 2 MCQs. So they knows how important it is, even a small fact, even a very small fact, even a very random thing. I talk about pseudo forces. I tell that now, and some points that we teach, it is the first and last time that we ever teach it again, right? We don't have time to repeat stuff. So some points that we teach, it's the first and last time. Goes with all three subjects, okay? Goes with all three subjects. Many points in A levels, you don't have enough time to revise stuff. So many points, it is the first and last time you are learning many points. So you should see a second shy batch class, that means a revision class. We can teach for 8 hours and they don't even, they are to like look away. They just stay focused, locked in. Why? They know that they missed engineering by 1 point. They know that they missed medicine by 2 points. Now they have to work for a whole year again, okay? Just because they missed 1 point, okay? Just because they missed 1 point. I mean, I can remember like at the beginning when we were teaching like multiplies and submultiplies, what is femtometer, what is attometer, you don't pay a lot of attention there, right? But I can remember there was a student who did second shy because one of the main lessons that he's doing is matter and radiation. He's really good at that lesson, okay? He's really capable in that lesson. So he usually get full marks from that lesson. That year there was like in the question, there was a term, the question is starting, the distance between two particles is 15 femtometers. Now the person can't remember what is a femtometer. Now he can't do the matter and radiation question. It is his main question. He usually choose that. So as a result, he loses some marks. He loses some marks, maybe 5, 6 marks, maybe 2 marks, misses engineering. Okay. He missed engineering by 2 ranks. That means engineering cutoff is, if it is 260, he's 262. Okay. If engineering cutoff is 260, is 262. As a result, person had to do second shy. So the second shy people knows how valuable it is, even a very single, very simple point. Okay. So, because I mean, you don't get this advice, you don't get to listen this advice in other classes. Okay. So keep this in mind in all your theory classes, many theory points, even simple stuff. Okay. Definitely for a certain amount of students, some theory stuff are too simple to listen. I know that. But in that too simple content, there will be one point that we mention only once in your whole A-level journey for 2.5 years, and you only get to see that again in A-levels, and you miss one MCQ, then it's done. Then it's done. Okay. So in all 3 subjects, one thing you should focus is never miss a point. Okay. Never miss a point. And this is the last day that we usually give this advice to. And like, because we see a lot of second shy students, okay, a lot of second shy students, and many of them are, I mean, medicine faculties are filled with second shy students. Why? You miss few points here and there. You miss, like, I mean, they take only 60 or 70 students to Colombo Medicine, right? Only 60 or 70 students. So you can't miss any point. 60 means you miss one MCQ, your rank goes by 80. Your rank goes down by 80 units, okay? From one MCQ, your rank can go down by 80 or 100 units. So all it takes is one MCQ, okay? So you should understand how important a simple fact is, okay? So I've seen like more than mid-level people, I have seen the people at the highest level, I have seen many of them doing second shy, more than mid-level people, because the mid-level people have to anyway struggle. So they never dare to miss a point. They keep locked in. They understand everything. They are not really smart, but the A-level paper is also not really smart. Okay, it's not a very smart, difficult paper. It's a bunch of points that you have to know. Okay, so you may be good at a lot of stuff. You may have a very good analytical thinking. Nobody cares. Okay, why? In A-levels, you miss one point, your analytical thinking have nothing to do there. Okay, so I have seen more people, more intelligent people doing second shy than the mid-level people. Okay, than the mid-level people. So everyone should stay focused. Okay, otherwise, I mean, it's like, it's still difficult to explain this. You have to do second shy to understand this, okay? Then only you would understand. You have to do the second shy to understand this. So in all 3 classes, all 3 subjects, even in paper classes, even in an extra class, even in a revision class, whatever you go, never dare to miss a point. In my class, the way I have assigned that is, when I'm doing simple stuff, I usually tell that do whatever you need. When I'm mentioning, okay, this is important, I have created that infrastructure, then you have to pay attention. So you can shift between doing whatever you need and listening in my class. I usually try to do that properly, but in all other classes, nobody does that. That means they would be telling very important facts, just like they are telling everything else, right? Okay, they will be telling a very important point, just like they are talking. Like, a lot of teachers don't emphasize, okay, this is important, this is important. It's not like that, okay? Especially the senior teachers, they don't emphasize. I'm in your age, okay, I'm close to age, so I know what happens in your mind. So I know if I don't tell that, okay, this is important, focus everyone, I know that that point will just pass through your mind. But especially the senior teachers, they don't do that. They don't, those days students didn't have ADHD. So those days, like, so senior teachers don't do that. Senior teachers don't do that. They just tell. They just tell. Then you miss a lot of points. Then you miss a lot of points if you are not listening. So if you are going to a class of a senior teacher, Never dare to talk for 5 seconds, okay? Never dare to do something of your own for 5 minutes. You will miss 1 point, then you will miss 100 ranks in A levels, then you will do second shy, okay? That's how it goes, okay? So keep that in mind. It's really important, okay? Okay, back to the lesson. And there are self-adjusting. Okay, pay attention. Now there are another type of forces is self-adjusting forces. What are self-adjusting forces? Uh, Self-adjusting forces are forces like this, like friction. Friction is okay. One thing is self-adjusting force is normal reaction. Normal reaction. That means when you're, pay attention, when you're standing on something, okay, when you're standing on the floor, you have your weight downwards, right? You have your weight downwards, right? Clear? You have your weight downward. Clear? Then why aren't you going down? Because Earth applies a normal reaction in upward direction, right? Earth applies a normal reaction in upward direction, which balance your weight. Clear? Clear? And your weight is mg. Your weight is mg. And definitely the reaction force from Earth is also mg. Clear? Reaction force from Earth is also mg. Clear? This is mg and this is mg. Clear? This is mg and this is mg. Clear? But I mean, you don't have like, we don't have an ideal weight, only those people can stand on Earth. It's not like that, right? Anyone can stay, no one goes down. Why? Why? Normal reaction is a self-adjusting force. Normal reaction is a self-adjusting force. That means if your mass changes, it changes accordingly. It changes accordingly. If your weight is 50 newtons, normal reaction is 50. If your weight is 100 newtons, normal reaction is 100. If your weight is 1000 newtons, normal reaction is 1000. Clear? So these kind of forces are self-adjusting forces. Clear? That means they adjust automatically. Clear? They adjust automatically according to the external force. Clear? They adjust automatically according to the external force. Clear? Then friction force, another self-adjusting force. Another self-adjusting force is friction. Friction. Friction is, again, assume like, if the object is not moving, what is, I mean, I apply 5 newtons. Due to friction, it's not moving. That means, what is the value of friction? 5 newtons, right? 5 newtons, clear? Then, you apply, you increase the force and apply 10 newtons. You increase the force and apply 10 newtons. Clear? Thank you. Still, the object is not moving. What is the reason? Friction adjusted itself for 10 newtons. Clear? So, friction is also an self-adjusting force. Clear? It adjusts itself according to the external force. Clear? It adjusts itself according to the external force. Then, like, yes, definitely, there's a threshold for the friction. There's a threshold for the friction. So when you pass that, it starts moving, okay? When you pass that, it starts moving, clear? Okay. So these are self-adjusting forces. These are self-adjusting forces. So these are the categories of forces, okay? These are the categories of forces that you should know. Okay. Okay, next what we have to do is we have to learn like Newton's laws, okay? Pay attention. Newton's laws, I think according to time, we will be able to finish the first law, okay? I'll take 15 minutes and finish the first law. That's all. And you have to write this in your book, okay? Take your notebook. Take your notebook. You know actually, right? You know the Newton's 3 laws, right? Okay. Take your notebook quickly, everyone. Or else take a piece of paper, write it and attach it to your tute, okay? Whatever the way you like. Take a piece of paper, write it and attach it to your tute. Because we are not going to write a lot. Only the Newton's laws part. Only the definitions I'm going to write. That's all. And like from today onwards, when like writing your name, write with your surname and school, because we are going to publish the marks, okay? Because that's why we started to make it proper, okay? The write in the paper and everything. And for online students also, we'll come up with a plan to make it more like accountable, to make accounts, like make marks more accountable. So when you're writing, write your name with the surname and your school, okay? Write your name, surname and school, okay? Okay, so pay attention. Newton's law of motion. Topic, Newton's law of motion. Newton's law of motion. චලිතය සඳහා වූ නිව්ටන් නියම. Newton's law of motion. Newton's law of motion. Quickly write. චලිතය සඳහා වූ නිව්ටන් නියම. Newton's law of motion. Stop talking, everyone. Newton's first law. Newton's first law. Newton's first law. Newton's first law. The reason to write this is you have to remember this, okay? That's why. Newton's first law. Everybody continues to be in a state of rest. Everybody continues to be in a state of rest. Everybody continues to be in a state of rest. Continues to be in a state of rest. Or to move with uniform velocity. Or to move with uniform velocity. Everybody continues to be in a state of rest or to move with uniform velocity unless a resultant force, unless a resultant unbalanced force, unless a resultant unbalanced force acts on it. Everybody continues to be in a state of rest or to move with uniform velocity unless a resultant unbalanced force acts on it. බාහිර අසන්තුලිත බලයක් වස්තුවක් මත බාහිර අසන්තුලිත බලයක් ක්‍රියා නොකරන විට වස්තුව නිශ්චලතාවයේ හෝ ඒකාකාර ප්‍රවේගයක පවතී. Don't write that, okay? I mean, I'm just mentioning because there are at least few students Sinhala medium. I know that. You don't have to write that again. You don't have to write a translation, okay? We are not doing this is not a translation class. වස්තුවක් මත බාහිර අසන්තුලිත බලයක් නොයද්දෙන විට එය නිශ්චලතාවයේ හෝ ඒකාකාර ප්‍රවේගයක පවතී. වස්තුවක් මත බාහිර අසන්තුලිත බලයක් නොයදෙන විට එය නිශ්චලතාවයේ හෝ ඒකාකාර ප්‍රවේගයක පවතී. Everybody continues to be in a state of rest or to move with uniform velocity unless a resultant unbalanced force acts on it. Attention. Focus, everyone. So the story is inertia, right? Inertia. That means unless you apply a force on something, it will stay in rest or it will move with a constant velocity. That's all. Clear? It will stay in rest or it will move with a constant velocity. Clear? That's all. Unless you are applying an unbalanced force. Clear? Clear? There was a nice proof to this. These are not mathematical proofs, okay? Attention. Lot of Newton's laws, okay? The mathematical proof came later. Attention everyone. They used it for years, okay? Lot of Newton's laws, they used it for years and the mathematical proof came later, okay? There are nice proofs related with Newton's laws because a lot of Newton's laws, he experimented by very simple experiments, okay? But this was first suggested by Galileo. This we call the Galileo experiment. A very simple experiment. That is, he used a system like this and placed a ball like this. A smooth surface like this. Clear? Now what happens? When you release it, it goes and returns to the same height, right? Attention everyone, returns to the same height. Now, you change the angle a bit. Clear? Then you place it here. What he identified was, this still returns to the same height. Clear? Clear? Definitely it is energy conservation. It's a different story. It still returns to the same height. Clear? Then he again decreased the angle. When he release, it again returns to the same height. We call these kind of stuff like maybe kind of thought experiments. After a certain point, these stuff becomes thought experiments. That means you keep doing this. Even for a very small angle like this, it to the height. Height is this. So, if you make this plane like this, then this will move until it returns to the same height. Since this is horizontal, it is never. When you really, if it happens for all angles, in this scenario also same thing would happen. It will return to the same height. Clear? But this scenario, it's never. That means ideally this motion should continue forever. Okay? Because it will move until it returns to the same height. Clear? And in this scenario, it's never, right? It's never. Clear? That means this object will move forever horizontally. That means unless there's an external unbalanced force, the motion of this object will remain forever. Clear? Unless there's an external unbalanced force, motion of this object will remain forever. It will move with the same velocity forever. Clear? Clear? So, lot of Newton's laws have nice like experimental proofs like this, okay? And like these kind of stuff, okay? These kind of stuff, they haven't asked us to teach these kind of stuff in the syllabus, but they always make questions from stuff like this, okay? Usually in all A-level questions, what they do is they link it with a application or a proof, okay? So there's a high tendency of you getting these kind of questions in mechanics, okay? Okay, so this is a 9. And the first question is, what Newton's law is, like what Newton's law is demonstrated here. What is the law? Newton's first law. What is the Newton's first law? Unless there's an external unbalanced force, the motion will remain. That's all. Unless there's an external unbalanced force, motion will remain. Clear? Then pay attention. Then when I'm like these kind of definitions, we have to pay very proper attention, because one term can change everything, okay? One term can change everything. So there are two terms that I used. External unbalanced force. To change the motion, you need an external unbalanced force. Why? Definitely unbalanced part you can understand, right? If you have an object like this, if you apply 5 newtons here and 5 newtons here, it will not move, right? So having a force is not enough. It should be unbalanced. Here it's balanced, right? Here you have 5 and it's balanced. Clear? You have 5 newtons in opposite directions and it's balanced. You remove this, then it will move. So you definitely need an unbalanced force. Clear? You definitely need an unbalanced force. Clear? Then the next part is uh, external. Why should it be external? Why should it be external? Force must be external. That means, assume that there's a truck like this, and you're here, and you try to push the truck. Can you do that? Pay attention, everyone. You are on a truck, and you try to push the truck. Can you do that? No. Why? Why? What is the reason? The person is in the system. The force the person is applying is not external. What actually happens is, I mean, you will understand this properly when we finish 3 laws, because the last law is every action has a reaction. For now, since it is from all levels, I'll use that. You apply a force on this truck. Clear? Assume 5 newtons. Then the track, this system applies you an reaction with the same value, 5 newtons. Now, due to these 5 newtons, you tries to move away, but friction stops that. Friction from this deck stops that. But the deck feels the reaction of that friction. Now you take the person 5 and 5 and the truck 5 and 5. See, you will understand this properly when we finish Newton's laws. But the thing is, internal forces, they balance internally. They solve the problem internally. So at the end of the day, there's nothing left for the motion of the object. Clear? If you are in the system, you can do nothing on the motion of the system. Clear? If you are in the system, you can't do anything about the motion. Clear? You can't do anything about the motion. Clear? Why? Why? You apply a force and the reaction is on you. Then again, to stop that, you use friction. Then again, the reaction of that friction again appears on the truck. So overall force on the truck is 0. See? Okay, you will understand this properly, but and again, like assume you're on a seat of the vehicle and you try to push the vehicle front forward, what happens? You apply a force on the front seat. What happens? Front seat applies a force on you. Then that force you apply on the back seat. Then the vehicle feels this one and this one. Nothing moves, right? Clear? That means if you apply 5 newtons and if you are in the system, okay, that's it, that 5 newton will return. Clear? It will return. Clear? Clear? So all the internal forces are all the internal forces disappears in the system. Clear? All the internal forces cycles in the system and they goes to zero at the end of the day. Clear? They goes to zero. Clear? Everything gets solved and go to zero. Clear? So there's no point of having an unbalanced force. Sorry, there's no point of having a balanced force. There's no point of having an internal force. Okay? What you need is external unbalanced forces. Okay? What you need is external unbalanced forces to move something. Clear? Clear? That's why. So you write the whole definition. You write the whole definition and you don't mention this external unbalanced part, you get 0 marks. Okay? You don't mention external, you get 0. You don't mention unbalanced, you get 0. Why? Definition is a definition. Okay? Definition is a definition. Part of a definition is not a definition. Okay? Part of a definition is not a definition. Then, and again, like towards the end, I'm going to do a small correction for these Newton's laws after teaching inertial frames. Okay? Then in each Newton's laws, we should write in an inertial frame, in an inertial frame, in an inertial frame. I'll explain that later. So, well, mobile phone. So, physical class marks. Well, we got these marks, right? We got these marks, right? Okay. Gavino. Gavino. 13. Tisul Ransana. Again, 13. Dinal. 13. Minuka Subasingha. Minuka Subasingha. 12. Sayumali. Did I tell that correct? No. Sorry? Okay, I said the same thing. Sayum. Sayumli. Okay, okay, okay. 11. Janiru. Savinula. 11. Sharon. 11. Sitija Sulochana. 11. Eron. 11. Tarul Gimet. What is the mark? Okay, we need that too. Tarul Gimet. Who's Tarul? Dunita. Dunita. 11. Tadeu Jayatilaka. Uh, and online marks, Indula Sahas 15, Naj Haris 14, Chamatka Jayavardhana 14, Patma 13, Chenita Matata 13. Yeah. So I'll start the paper discussion around 7:30 maybe. I'll start the paper discussion around 7:30. And for new students, usually there's a paper before the class and paper discussion happens after the class. You can join it when you're comfortable, okay? You can join it when you're comfortable. So I'm going to stop it here. Pay attention. I'll be doing an extra class tomorrow, most probably. For a term test paper, okay? We'll start term test paper discussions tomorrow. And mechanics from beginning sessions will happen on Sundays for now, okay? Mechanics from beginning sessions will happen on Sundays. Thank you. Okay. Tao me. Uh, like, first of all, mention the question numbers that I should discuss. Quickly write on a paper. Quickly do write on a paper that I should discuss. Quickly do write the question numbers that I should discuss on a piece of paper and hand it out to me. And online students, mention them in the Zoom chat. Mention them in the Zoom chat. Okay, please be seated quickly, and online students mention the question numbers that I should discuss. Mali, can you put the paper in the Zoom chat? Mali. Mavidu. Yeah. Chenide. Put the papers on the Zoom chat. I think I'm going to get the whole paper at the end of the day, right? And again, there have been a small mistake. I mean, we have missed a set of papers and we have the best marks there eventually. So, attention, Chiran, who's Chiran? 15. We have to read these marks again. Nisila, again 15. Sasen Pereira, 12. I think I anyways have the whole paper here, right? Anyone else? Okay, sorry. Okay. Attention, everyone. Only a paper. And anyone in the physical class who don't have a paper? Anyone need a paper in the physical class? Yes? Yes? Okay. Few papers there. Thank you. Okay. Question 13. Question 13. A ball is projected upward. A ball is projected upward at an angle theta with a speed of 25 meters per second. a wind blows in a given direction, producing an acceleration of 5 meters per second on the ball in the direction of the wind. Find the value of theta so that the ball returns to the point of projection. Find the value of theta such that it returns to the point of projection. Thank you. Okay. So today we are discussing the model paper 38. Model paper 38. The idea like this. We project like this. Pay attention. We project it like this. Model paper 38, question 13. We project it like this with an angle of theta. With an angle of theta. Then, with a speed of 25. With a speed of 25. A wind blows in a given direction, producing an acceleration of 5 on the ball in the direction of wind. There's an acceleration of 5 in this direction. There's an acceleration of 5 in this direction. Acceleration is 5 in this direction. Find the value of theta so that the ball returns to its point of projection. So we need to find theta. How can I do that? Let's apply equations in. So it goes like this and returns to the initial position. That means upward displacement is 0 and horizontal displacement is also 0, right? Both vertical and horizontal displacements are 0, right? Both vertical and horizontal displacements are 0. Clear? So, if I apply equations in this direction, S equals ut plus half at squared. S equals ut plus half at squared. Displacement is 0. Starting vertical velocity. 25 sine theta, right? 25 sine theta. 25 sine theta. Starting vertical velocity is 25 sine theta. Into time it takes to return to this point. So we release it at t equals 0. It returns to this point at t equals capital T. Plus half. In vertical direction, acceleration is minus 10. Acceleration is minus 10 into t squared. Then I'm going to get 0 equals, I'll take t out. Then 25 sine theta. 25 sine theta minus 5 into t. Minus 5 into t. So you have t equals 0. You have t equals 0 or 25 sine theta minus 5t equals 0. That means t equals 5 sine theta. When you solve this, you take everything to that side. That means 5t equals 25 sine theta. 25 sine theta. Then t equals 5 sine theta. T equals 5 sine theta. So this is in vertical direction. Then in horizontal direction, again same thing. Again same thing. S equals ut plus half at squared in horizontal direction. So the horizontal displacement is 0. Horizontal displacement is 0. Horizontal velocity 25 cos theta. Horizontal starting velocity 25 cos theta. 25 cos theta. Time capital T plus half. Acceleration is minus 5. Why? Attention. There's an horizontal acceleration in this direction due to wind, right? Now there's an horizontal acceleration in this direction due to wind. Clear? So you should put minus 5. Clear? You should put minus 5. Half minus 5 again t squared. T squared. Clear? Then again 0 equals t 25 cos theta. 25 cos theta here minus 5 over 2 into t. Then you get two answers, t equals 0 or this is equal to 0. 25 cos theta minus 5 over 2t equals 0, which means t equals, I'll take this here, so 5 over 2t equals 25 cos theta, 25 cos theta, 5 over 2t equals 25 cos theta. Then this cancels out, 5. Then you take this 2 here, t equals 10 cos theta. T equals 10 cos theta. Clear? So I apply equations vertically and horizontally, and both vertical displacement and horizontal displacement 0 in this case, right? Both vertical and horizontal displacements are 0 in this case. Both are 0. Both horizontal and vertical displacements are 0. Then what you can do is, and it returns to the starting point at the same time, right? It returns to the starting point at the same time. That means this t and this t is equal, right? This time and this time is equal, right? Clear? That means what is this time? 5 sine theta. 5 sine theta. Then what is this time? 10 cos theta. 10 cos theta. Then sine theta over cos theta is tan theta. Sine theta over cos theta is tan theta equals what? You keep sine theta here and bring cos theta here, then you get tan theta, then 10 over 5, which is 2. Which is 2. So tan theta is 2. That means theta is tan inverse 2. 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 You can write this later. I'll provide the review in the WhatsApp group, okay? I'll provide the review in the WhatsApp group. You can use the review to write it down. So for now, listen properly, okay? For now, listen properly. You can write things later using the review, okay? Review will be given in the WhatsApp group and in the website too. So you get the same time. Pay attention. It returns to the starting point at the same time. It returns to the starting position at the same time. So you use that to create a relationship between sine theta and cos theta. Clear? Clear? Then question 14. Question 14. You apply equations vertically, make displacement 0. Pay attention. You apply equations horizontally and make displacement 0. Then you get the overall answer as theta equals tan inverse 2. Clear? Clear? You apply equations vertically and make the displacement 0, and you apply the equations horizontally and make the displacement 0. Vertical displacement, vertical acceleration is minus 10, horizontal acceleration is minus 5. Then you get two answers for t, but it is equal. So you use that to create a relationship between sine theta and cos theta. Clear? Clear? Okay. Question 14. A train is moving along a straight track with constant acceleration. A child inside the train throws a ball forward at an angle of 60 degrees to the horizontal with a speed of 10 meters per second relative to the train. And I think 1 or 2 corrections were done on the board, right? Just let me know if I go through a question like that, okay? To catch the ball at the same height from which it was thrown, pay attention, the child must move 1.15 meters forward inside the train. Find the acceleration of the train. So actually the train should be decelerating, right? Yes, train should be decelerating. We'll see. So it's like this. It's like this. Question 14. You are in the train. You are in the train. You are in the train. Now let's take the velocity of the train as u. Velocity of the train as u. And you are throwing something with a velocity of 10 relative to the train. So you are throwing something with a velocity of 10 relative to the train. This velocity is there relative to the train. It's there relative to the train. Then what is this angle? What is this angle? This angle is 60 degrees. Then you have two components. One is 10 cos 60, 10 cos 60. And this component is 10 sine 60. 10 sine 60. Which means 10 cos 60 means 10 into cos 60 is half, which means 5. Mali, can you put the paper in the WhatsApp group too? It's available in the WhatsApp group, right? Yeah. Put the paper again in the Zoom chat. So the velocity is 5. Horizontal velocity is 5. And what is this velocity? 10 sine 60. Sine 60 means root 3 over 2. Sine 60 is root 3 over 2, which is 5 root 3. 5 root 3. So this velocity, pay attention, this velocity is relative to the train, right? This velocity is given relative to the train. So to get the actual velocity, you should add the velocity of train to this, right? Clear? If this velocity is relative to the train, to get the actual velocity, you should add the velocity of the train to this, right? So the actual velocities of this wall would be, in this direction it's still 5 root 3. In this direction it's 5 root 3. In this direction it's not just 5. It should be 5 plus u, right? Why? Train has a horizontal velocity. Train has a horizontal velocity of u in this direction, right? So if this velocity is given relative to the train, to get the actual velocity, you should add the velocity of train to that, right? To get the actual velocity, you should add the velocity of train to that, right? Now only I have velocities relative to ground. Clear? Pay attention. Now only I have velocities relative to the ground. Clear? Okay. Then it will move like this. Now what about the person? What about the person? He's with the train, right? So the person's starting velocity would be u. Why? Velocity of the train. Clear? And the person will feel a horizontal acceleration a, because they are telling that the train has an acceleration of a, right? Train has a acceleration of a. Clear? So for the person, starting velocity is u, same as the train, but train is accelerating, so the person is also accelerating. Clear? But after you throw this one, it's not accelerating, right? Why? It's just going as a free object, right? It's not connected with the train anymore. After you throw this thing, it will freely move, right? It will freely move as a projectile. Clear? It will freely move as a projectile. Now, okay. So what I could do here is, I can use the time to connect them, okay? I can use the time to connect them, but if I assume, I think we'll be able to do this, right? I hope I don't have to go through the like time. We'll see. If this starting time is 0, if this starting time is 0, if this time is capital T, it will take a time t for this sphere ball to go here. Clear? And to catch this, the person should reach here at the same time, right? Person should reach here at the same time. Clear? But they are telling that it is not enough. They are telling that it's not enough. They are telling that it's not enough. As a result, person have to move an additional distance of, as a result, the person has to move an additional distance of 1.15 meters forward. Clear? So the person is on the train. Person is on the train. So using the motion of the train, person will move from here to here. Clear? But they are telling that it's not enough. It's not enough. As a result, person have to move an additional distance of 1.15 meters to catch that. Clear? So, let's hope we don't have to find the time, but if we have to find the time, we can easily get that. Okay. I'll apply S equals ut plus half at squared. So, for this wall, displacement would be, S1 would be horizontal starting velocity 5 plus u. Horizontal starting velocity 5 plus u. Horizontal starting velocity is 5 plus u. And the time it takes to land is capital T. And there's no horizontal acceleration because it's moving freely. There's no horizontal acceleration. Then for the other object, that means the person, for the person, S2 is S equals ut plus half at squared. Starting velocity of the person is u. Time taken is capital T plus half acceleration of a squared. So this distance is S1. This distance is S2. So S1 equals this distance S2, this distance S2 plus additional 1.15. Why? The person have to additionally move a distance of 1.15. Clear? So S1 equals S2 plus 1.15. Clear? Clear? Then what is S1? This is S1, right? S1 is 5 plus u into t. What is S2? This is S2. ut plus half at squared plus 1.15. Then you have here 5t plus ut equals ut plus half at squared plus 1.15. So this ut and this ut may cancel out. Clear? I mean, you could have done the whole question without considering u only for relative motion, okay? I'm just going in the much clearer path, not the easiest path, okay? I'm going through the clearer path, not the easiest path. Easiest path would be just forget u for both train and the ball. Why? It's relative. So relative components you can remove from the system, right? It's easy to remove relative components from the system and do the question. But I'm going through a much clearer part at the moment, not the shortest path, because we have just finished this content. But within few weeks, I'll give up the clearer path and choose the shortest path always for questions, okay? By then, you should have the capacity to understand them, okay? So what you should do is go home and try these questions few times, watch the recording again and again and try to understand. Then when you can understand the much clearer path, then we can forget the clear path and always try to get the answers using the short path, okay? That is my plan, okay? Okay. So you have this, so definitely you have to find the time, right? Definitely you have to find the time and then you can find the acceleration, right? So here you have 5t equals half at squared plus 1.5. Now how can I find the time? Apply equations for the vertical motion. It's the time of flight of a projectile, right? Time of flight of a projectile. I mean, we can directly use the equation. Can you remember the equation for the time of flight? I have asked you to remember these things for MCQs. 2u sine theta over g, right? 2u sine theta over g. Can you remember? This is the time of flight of a projectile. Time it takes for the whole projectile. So you have 2. What is u sine theta now? U sine theta is this, which is 5 root 3, right? U sine theta is 5 root 3. Then G is 10. G is 10. Then this 2 and 5 and this 10 cancels out. You are left with root 3. You are left with root 3. Clear? Then you can bring that root 3. Then you can bring that root 3 into this. Clear? 5 into time root 3 equals half acceleration, then root 3 squared plus 1.15. Clear? Clear? 5 root 3 equals half a root 3 squared plus 1.15. Clear? Now only unknown is a. You can solve this and find a, right? Now the only unknown is a. You can solve this and find a, right? So a would be 5 root 3 minus 1.15 over this one. When you solve 3 is 3a, 3a. So 5 root, I'll take 1.1 here, then multiply it by 2 and divide by 3 and solve this. Clear? And solve this. Clear? And root 3 and everything is given, okay? So you should be able to do the calculation. Clear? Clear? So the method is just apply equations for the projectile, apply equation for the train, and they are telling that the person have to go an additional distance of 1.15. Clear? That means this distance equals distance of the train plus additional 1.15. Clear? This gives you the full answer. Clear? Okay. So again, I repeat, like, I'm not gonna usually like explain really. can do is watch the and try to understand him, because like the paper discussion is mainly targeting your speed, okay? Speed of understanding. Okay. Let's move to question 12. And there's a issue in question 15. It's not that it's not wrong. I could discuss a lot of stuff about 15. So if I'm not able to do question 15 today, I'll do a short video and upload it to the group, okay? Because 15 is a lengthy question which we can use different methods and get, like, we can get a very quick answer, or we can choose a lengthy path, okay? There's a lot to discuss in question 15, that's why. We'll see. If time doesn't permit, I'll provide a recording for question 15, okay? It's a nice question. An object is projected. Question 12. Question 12. Question 12. An object is projected. Yeah. Okay. An object is projected from a point A at an angle of 45 with a velocity of v1. At the same instant, another object is projected vertically upward. Stop talking. From point B with a velocity of v2. Point B lies directly below the maximum height of the trajectory of the object from A. The ratio of v1 over v2 for the two objects would be. So answer should be root 2, right? Answer should be root 2, right? Why? Okay. Pay attention. Now, it is v1. This object has a separate horizontal motion, v1 cos 45, separate vertical motion, vertical motion, v1 sin 45. Clear? Then there's another object. There's another object B. I throw it with a velocity of v2. Now, they reach the same vertical point at the same time, right? That's what they are telling, right? In the question. They are reaching the same vertical point at the same time, right? Clear? Yeah. Pay attention, everyone. Pay attention. So if they collide, okay, I throw something like this and another object like this, but they collide. That means they reach the same vertical height at the same time. they reach the, stop talking, they reach the same vertical height at the same time. That means their vertical motions are equal, right? That means their vertical motions are equal, right? Clear? So if their vertical motions are equal, their vertical starting velocities should be equal, right? If they reach the same vertical height at the same time, they reach the same vertical height at the same time, right? For that to happen, their vertical motion should be equal, right? For that to happen, their vertical velocities should be equal. So for this person, vertical velocity is v2. For this person, vertical velocity is v1 sine 45. v1 sine 45, clear? Then you are going to get v2 equals v1 sine 45 means, 1 over root 2, right? Sine 45 means 1 over root 2. Is v1 over 2 is v1 over v2 is v1 over v2 is root 2. Clear? Clear? Question 8. Question 8. You can write this later. Pay attention. Pay attention. An object is released from rest from height h. After hitting the ground, it rises to a height of h over 2. The graph, which graph best shows the variation of object's velocity with height is. Okay. So we have a graph of velocity and height. Okay. Now, so you release it like this, okay? You release it like this. Now the height is h. Pay attention. Now the height is h. So you are starting from height h. You are starting from height h, but 0 velocity. Velocity is 0, height is h. You are starting here. Clear? Then your velocity increases and velocity reach its maximum. Velocity reach its maximum when? Velocity reach its maximum when h is 0. Clear? That means when h goes to 0, see? When h goes to 0, velocity increases. Velocity increases. When h goes to 0, when h goes towards 0, velocity increases, right? Clear? When h goes to 0, velocity increases. Clear? Now what happens is, it bounces back. It bounces back. Clear? It bounces back, but this time it reaches a maximum height of h over 2 only. What is the reason? What is the reason? It loses some velocity. Clear? Reason is it loses some velocity. Clear? Now velocity is in this direction, velocity turns into the opposite direction. Clear? So if the velocity was positive, now the velocity should be negative, right? But it bounced back with a lower velocity. Clear? So if this was 5, this value should be lower than 5. Clear? This should be lower than 5. Like this. Clear? It should be lower than 5. Clear? Then Now height increases, velocity decreases. So when height goes to h over 2, when height goes to h over 2, again velocity goes to 0, right? Again velocity goes to 0. Now when height goes to h over 2, again velocity goes to 0. Clear? This is the curve. Clear? This is the curve. Clear? Question 7. Question 7. 7 again. What is the change? All answers were changed. Then let's do the calculation and see the answer. So question 7 was changed, right? Question 7 was changed during the session. A car starts from rest and moves with an acceleration of 2. So a car starts from rest and moves with an acceleration of 2. There's a car, acceleration is 2. There's a car and the acceleration is 2. Distance is 600 meters. Distance is 600 meters. Then it continues to move the remaining 200 meters with a uniform velocity. Now it moves the remaining part with a uniform velocity. So this car starts from 0 velocity. Car starts from 0 velocity and accelerates with 2. Then it gains a certain velocity and move remaining 200 meters with that uniform velocity. Travel the remaining 200 meters with that velocity. What is the total time taken? This is t equals 0. This is t equals capital T. Then I'm going to apply v squared equals u squared plus 2as from A to B. From A to B. Final velocity v. Pay attention. Stop talking. Starting velocity 0. Starting velocity 0 plus 2. Acceleration is 2 and distance is 600. Distance is 600. Distance is 600. V equals 4 into, this is 4 is 2 squared. Then this is 6 into 100. 6 into 100. V squared equals 2 squared into 6 into 100. Then V is, when you get the square root, 2 squared becomes 2. 6 becomes root 6. 100 becomes 10. So the velocity is 20 root 6 meters per second. Velocity is 20 root 6 meters per second. Clear? Then it travels the remaining distance with this velocity. It travels the remaining distance and I can apply from here to here. Attention everyone. Stop talking. I can apply V equals U plus AT. Pay attention. I can apply V equals U plus AT from here to here. Final velocity is 20 root 6. Final velocity is 20 root 6. starting velocity 0, acceleration 2, and time is t. And time is t. Then t is 10 root 6. Time is 10 root 6. Clear? Then this is from A to B. Then I'll apply from B to C. S equals ut plus half at squared in this direction. Displacement is 200. Starting velocity v, which is 20 root 6. Here the starting velocity is 20 root 6 because the velocity here is 20 root 6. So the velocity is 20 root 6. Time I have to find. And acceleration is 0. Acceleration is 0. So you get t equals 200 over 20 root 6, which gives you 10 over root 6. So the total time is time from here to here, 10 root 6. Remaining part is 10 over root 6. 10 over root 6, clear? Then you have to find root 6 and do the calculation, right? You have to find root 6 and do the remaining calculation, clear? Clear? Okay. So definitely bring the logbook, okay? Definitely bring the logbook, okay? Every week, definitely bring, so class is not over. Every week, definitely bring the logbook, okay? Because otherwise you can't survive some questions, okay? Question 9. And one more thing. Go to question 4 a bit. Go to question 4. In question 4, they mentions, pay attention. Pay attention. Pay attention. In question 4, it mentions to measure the volume of a solid sphere, a micrometer screw gauge is used to take two readings perpendicular to each other, as shown below. Calculate the volume of the sphere. I think some may have, you got the correct answer for this, right? So definitely some may have taken the wrong answer, assuming that we are measuring the radius. We can't measure the radius using using a micrometer screw gauge, right? You can't measure the radius using a micrometer screw gauge, clear? What you can measure is the diameter, okay? What you can measure is the diameter, clear? Clear? So the reading is 10, 11, 12, 12 millimeters plus 31, I think, right? 31 into 0.01 into 0.01, which means 12.31, clear? And in the second scenario, it's 12 plus. Usually what we do is we measure like this, then like this. Then it is 12 plus 50, 51, 52. It's 55, right? 55 or 54? right? It's 55 into 0.01, which gives you 12.55. Then you get the mean value, right? You add these two. And divide by 2. And divide by 2. You get the mean value. 12.31 plus, pay attention, 12.55 over 2. This gives you 12.43. This gives you 12.43. Clear? Now you should understand, what is this? This is the diameter. To find the radius, you should divide this by 2. Clear? You should divide this by 2. You get something like 6.215. Clear? Now only you can find the volume, right? Now only you can find the volume. What is the equation for the volume? 4 over 3 pi r cube, right? 4 over 3 pi r cube. Clear? So the volume is 4 over 3 pi. Pi is 3. Pi is 3. R radius is this 6.215. 6.215 cube. 6.215 cube. Clear? Clear? So I think, and later you have to get this is, you get the answer in millimeter cube here, then convert it into centimeter cube. Okay. So a lot of students I think you didn't get the answer, right? Because you thought that it's the radius, right? You can't measure the radius using a micrometer screw gauge. You can only measure the diameter. Clear? You can only measure the diameter. Clear? That's the reason. Question 9. Last question. I'll take 2 minutes and finish this. So the mistake here is, this is the diameter. Then you get the mean value for diameter. Then you apply this for the equation. That's all. Question 9. This is an acceleration time curve. Acceleration is 2 for 1 second. Then acceleration is minus 2 for 2 seconds. Then acceleration is again 2 for 1 second. 7 to 8. 7 to 8. Clear? So they are asking the maximum velocity, right? So I think maximum velocity should be 2, right? Pay attention. Maximum velocity should be 2, right? Why? We know that the velocity is the area of the graph, right? Velocity is the area of the graph. So what is this area? 2 into 1, which is 2. So after 1 second, velocity is 2. Clear? Then again we have a negative acceleration. So there, the velocity changes. What is this area? What is this area? It is minus 4, right? Then we have to think about that, right? Did we consider that? Okay. Then we have to consider the direction here, right? Yeah. Because, pay attention. Now the velocity difference is 2, right? Pay attention, everyone. Because the area is 2. Area is 2. Clear? Area is 2. That means velocity difference is 2. Clear? Then, what is this area? 2 into 2, which is minus 4, right? Minus 4. Then no change. Velocity changes from minus 4. That means now velocity is 2. If the velocity decreases by minus 4, what happens? From 2 to it goes to minus 2. Why? From 2, velocity difference is minus 4. So you go to minus 2. Clear? Then, again, from 7 to 8, area is 1, right? Area is 1. So the next part, sorry, area is 2. Sorry, no, it's again 2 into 1. This is 2, right? So this height is 2. This is 1. That means now the area is 2. Clear? That means again velocity difference is 2. That means from here to here, velocity increases by 2. Minus 2 plus 2 equals 0. So in the whole journey, we start with 0. Then the velocity becomes 2 after this area. Then the velocity becomes minus 2 after this area. Then velocity becomes 0 after this area. Clear? So throughout the whole journey, what is the maximum velocity that I obtain? Throughout the whole journey, maximum velocity that I obtain is 2, right? So maximum velocity is 2. So I have to discuss question 15. So what I would do is, I would provide a recording for that. I have 1 or 2 more questions here. I'll discuss that question in tomorrow's evening session, or I'll provide a recording, okay? I'll discuss question 15 tomorrow evening extra class. I'll mention the time and everything. Please set up your websites. I'll do that tomorrow evening, or I'll provide a recording for question 15. Thank you.